This is the second part of the module, energy analysis for open systems, control volumes under steady state, steady flow conditions. We have the general equations for conservation mass 531 and general equations for the conservation of energy 537 without any other assumptions besides the steady state, steady flow conditions for multiple inlets and multiple exits. For a single inlet entrance and a single exit, 531, 537 reduced to simple versions of 532 and 538, so single inlet. And we have this which we can apply to our engineering devices with further assumptions made. Here there's a simple schematic diagram of a control volume, but m dot in here represents the total mass flow rates from the multiple inlets, and m dot out is the total mass leaving from the multiple exits. Meanwhile, W dot out is just the net work out, that means work done by the system, and the heat interaction is coming into the system. This is positive. This is how 538 represents the energy interactions that crosses the boundary of your control volume. We look at first the nozzles and diffusers. Yeah? A nozzle is a device that increases the velocity of a fluid at the expense of pressure. The cross-sectional area of a nozzle decreases in the flow direction, and thus the velocity at the exit is increased much higher than that at the inlet. For subsonic flows, which we shall consider only in this course. A diffuser, on the other hand, increases the pressure of a fluid with decreasing velocity. So the cross-sectional area of a diffuser increases in the flow direction for subsonic flows. So when we analyze the mass and energy balance for nozzles and diffusers with one inlet and one exit, mass flow rate is constant, so you can just use m dot without any subscript. Heat interaction is negligible because there isn't enough time for heat interactions to occur during the flow, but they are sometimes considered. So you have to be careful when you perform your thermodynamic analysis what crosses the boundary. Work interaction is typically zero because there's no work crossing the boundary. And the change in potential energy is negligible. However, the change in kinetic energy is significant and must not be ignored. Now, the conservation of mass and energy for nozzles for single inlet and exit reduced to this. You can just use m dot, and the conservation of energy reduced to this form for any fluid. Now, what do you do with this equation? And normally, you will be asked to determine the velocity at the exit of a nozzle or the enthalpy at the inlet. And how do you determine the enthalpy? Well, you may use the two property rule. If you know the pressure and the temperature at the any location, you may determine other properties. For ideal gas, you may substitute the change in enthalpy with Cp average change of temperature for ideal gas only. Next is the turbines and compressors. Turbines produce work when the working fluid passes through them, undergoing an expansion process, pressure drop, in a turbine. For compressors, as do pumps and fans, they require work to increase the pressure of the working fluid. Schematically, when you sketch a diagram of a turbine, it should have that form and a compressor that form. Compressors are used for gases and pumps for liquids, while fans are generally used to mobilize gas. So in analyzing the mass and energy balance for turbines and compressors, heat interactions is approximately zero because they are insulated to reduce eliminate heat loss, except when compressors are used with intentional cooling. Change in potential energy is negligible. Change in kinetic energy is negligible, except for turbines, though sometimes they are also neglected. Now, if you look at the conservation mass and energy for turbines and compressors, and knowing this information, so you have your equations just reduced to these forms. So conservation of energy is just this, with the heat interaction assumed to be going into the system. minus the work interaction done by the system, and equal to the mass flow rate multiplied by the change in the enthalpy for any working fluid. If you have a gas, expansion in a turbine or compressed in the compressor, you may replace the change in enthalpy with the Cp average delta T only for ideal gas. Now the term summation must be used if your turbine or compressor involve more than one inlet or one exit. Throttling valves. Throttling valves are any kind of flow restricting devices that cause a significant pressure drop in the fluid. Schematically given here: adjustable valve, a porous plug, or a capillary tube. Now, pressure and temperature of the working fluid drops as it passes through a throttling valve, almost like the diffuser, right? But the analysis is different because throttling valves are often used in air conditioning and refrigeration systems. In analyzing the mass and energy balance for throttling valves, we have heat interaction approximately 0. There isn't enough time for heat interactions to occur, and the devices themselves are all small. Work interaction is 0. If you look at the boundary, you have to determine the boundary of your control volume. Change in potential energy is negligible. Change in kinetic energy is negligible. So your conservation mass and energy for throttling valves are now reduced to just this form. So in the end, you just get the enthalpy at the exit approximately equal to the enthalpy at the inlet. It's like an isenthalpic process for any fluid, right? So if you have ideal gas, you may replace the change in enthalpy, which is equal to 0, equal to the C average delta T. In the end, you get T2 is equal to T1 for ideal gas only. Now, you think, what about the change in internal energy? Can you replace that with CV average delta T? Or can you use PV P1 V1 is equal to RT1 and P2 V2 is equal to RT2? Think about that. Yes. Next engineering device is a mixing chamber, where the section where more than two streams are mixed, is a chamber. And the chamber is not necessarily a tank or a proper chamber, but it just could be a T elbow or Y elbow where hot water and cold water are mixed, like the one you have in the shower, right? So here I have labeled inlet 1 as A, inlet B, second inlet as B, and the outlet as 2. So in analyzing the mass and energy balance for a mixing chamber, again, your system should be well insulated so as not to lose heat to the surroundings. Work interaction is typically 0. Change in potential energy negligible. Change in kinetic energy is also negligible. And so you have your conservation of mass and energy for a mixing chamber reduced to these two forms. So I like to label my multiple inlets as A and B, and my exit as 2. It's easy to remember. Your ebook label it as 1, 2, and 3. It's up to you what numbers you want to use, what labels you want to use, just so you make sure you know which one means what. Yes. And heat exchangers. Heat exchangers are devices where two moving working fluid exchange heat without mixing. Yes. In the mixing chamber, the mixing occurs with the two stream mixing in the chamber. Here is kind of a mixing chamber but without mixing. There are many designs for heat exchangers and two ways to analyze the control volume. Case A, you analyze the whole system, both streams, and case B, you analyze either one of the streams. Now, the streams can be both liquid or one of them could be gas. In analyzing the mass and energy balance for a heat exchanger, work interaction is typically 0. Change in potential energy is negligible. Change in kinetic energy is negligible. But for the heat interaction, for case A, it's 0 because you would like the heat exchange to occur only between the two streams and not with the surrounding. For case B, for each stream, there is heat interaction because whatever heat is gained by one stream must be lost by the other. Exactly equal in magnitude but not in direction. So the conservation of mass and energy for a heat exchanger is now reduced to just these two forms. For case A or case B, the conservation of mass is the same. Mass flow rate of A is not the same as the mass flow rate of B. The different streams. Yes. But for the energy conservation, they are different. If you analyze both streams together in your control volume, you will get it in this form. But if you analyze only one stream, doesn't matter which stream, it will be in this form. Again, your Q for stream A is equal to Q for stream B in magnitude, but opposite direction. So if one is positive, the other must be negative. And finally, pipe and duct flow. Working fluids or of liquids or gases are generally transported in pipes and ducts. So in analyzing the mass and energy balance for a pipe or duct, consider that the heat interaction depends on the application. It is significant if the purpose is to exchange heat, but zero if just to transport, generally it's insulated. We assume perfectly insulated. Work interaction should be considered if it involves a heating section, a fan, or a pump shaft. But if nothing crosses the boundary, then work interaction is zero. Change in kinetic energy is negligible because the cross-sectional area is generally equal at the inlet and exit. The change in potential energy is negligible unless it involves large elevation from the inlet to outlet. Like, you're trying to pump a certain amount of working fluid from one elevation to another. Then you have to consider the change in potential energy. Now, the conservation of mass and energy for a pipe and duct, single exit and single inlet, is now simplified to just this equation. Again, if you look at the conservation of energy, if there is no work interaction, then this term is zero. There's no heat interaction, this term is also zero. And if the pipe is horizontal with the same cross-sectional area in the inlet and outlet, this term would be zero, and you end up with just this term. So that wraps up thermodynamic analysis for commonly used engineering devices for this course.